It's a set of tools that let you analyze traffic on your website, and it comes about basically some of it's server side and some of it is a little bit of JavaScript code that you put on your web pages. A whole other interesting question is, should a website actually display an ad at all?
A capstone course is different from a regular course. You do one project over the entire quarter. You're usually trying to build something brand new that's never been done before. As opposed to in normal classes, your homework assignment has usually been done by lots of people every quarter. And so the capstone is a chance to try something new and bigger and has a wider scope. This time you're doing something brand new of your own design. Advanced Internet Systems usually focuses on how to design and build search engines, something like what Google does to crawl the web. This quarter we're doing things a little bit differently, specifically focusing on the problem of information extraction. And so given some news article or piece of text, our system will try and extract from that all of the facts.
There's sort of two approaches. You've got the sort of global relevance in the search engine retrieval sense, and you could basically have some sort of threshold, and if it's not above that threshold, you shouldn't show the ad. Another thing is you can actually build a classifier and try to predict, is somebody going to click through on this ad? And that approach naturally tends to work better.
Based on what's called the TAC KBP challenge, which is basically, there's a number of slots to fill, slots of information. A person is born in some country, or a person was born on some date, or an organization is headquartered in some country, or this event occurred on that date. Okay, so these are the pieces of information that we're trying to extract. Anything that is co-referenced with one of those entities also is annotated. And the goal of the course is to divvy that project up into a number of different pieces. Our particular piece is we're given a piece of text and we're trying to do the first part of the problem, which is to find the entities that exist. So people, Barack Obama, Hillary Clinton, the new Pope. So we're trying to identify those mentions and then link them to Wikipedia articles so that we can basically get a unique identifier for each entity. So Bill Clinton has ID number 3,102,000. And then that will allow us to distinguish between different Bill Clintons.
We began over the course of the quarter a tale of two fillers. Tim made a T-regex filler. Can anyone guess what the T stands for?
Tim.
Tree. Although it can stand for Tim as well. We ran these fillers over the entire corpus to answer a list of queries about organizations or people and accumulated the possible answers, and then we picked the most popular one.
The filler I was working on was just a standard regular expression approach. If it found those, then it would search for a couple different regular expression keywords and patterns.
And over the course of the quarter, our workflow pretty much looked like this. We split the training data into 3 sets. A training set, which we started with when we started developing our fillers, and then a development set, which we use as test data. And we measured the recall precision in the F measure in order to evaluate our algorithm's performance. To wrap up, we had actually some more significant aspirations earlier on in the quarter, but things like machine learning and the Wikipedia data would have been nice to use. It would be good for precision, but not necessarily recall. And also, MapReduce took longer than expected, so our final data will be in our paper. That's it.
Okay, thank you.
These entity dimensions can be anything. They can be strings, uppercase, lowercase, multi-word strings. The searcher's job is to generate candidates, which are Wikipedia URL names that the mention can be referring to.
So Dan suggested we take this data that a Google Stanford team had generated, basically like 300 million pairs of mentions to Wikipedia articles, plus probability that the given mention was talking about that Wikipedia article. So we used that to generate candidates, and it gave us much better results.
We wanted to do everything ourselves, or as much as possible ourselves. So we wrote Orson, which we found from some baby names website online. We put together this code base in Scala and with a MongoDB backend because it scales right up.
We had big aspirations. We were thinking we could release this as a library online. So we used 2 sources of data, sentences, Stanford, NER. So NER tags, these are person tags.
As opposed to the Davids who were trying to generate all the possible senses for a given mention, our focus was on disambiguating to find the correct sentence.
So we decided what we were going to do is base our system on an existing system by two guys named Milne and Witten. And they have an entire pipeline for extracting mentions, finding possible senses, and then disambiguating. So what we did is we added IDF support.
The other idea was that use an existing co-reference system. The Stanford people put out one that will find all the co-reference entities in an article. After we do entity linking the first time, we'll apply co-reference, then do entity linking again, and then see if anything's changed, and keep doing that until nothing changes. And hopefully that will give us better results.
And what did we find? So the prior score is on the left, and then our system is on the right, and the Milne and Witten system is in the middle. So this was kind of confusing. So not only is our system, our system is a little bit better than the Milne and Witten, but both are worse than just the dumb approach, which was kind of frustrating. So we were like, okay, why is this? So when we test on Wikipedia rather than on these manually annotated articles, we find that the disambiguator does much better than the priors.
We learned that working with these big data sets takes a lot of time, and if we had to redo this, we would definitely have left ourselves more time because it took so long to run our systems. And your choice of data set is very important, as Melissa's already enumerated reasons for that. But it is really cool when we can successfully annotate things. Anything to add?